audio recording for the visualization. Chapter 1 Atomic Structure, and the introduction is one of the earliest models of atoms were proposed by Rutherford. According to the Rutherford model, most of the mass of an atom is concentrated in a small dense nucleus. The electrons are revolving around the nucleus and occupy most of the volume of an atom. The nucleus of hydrogen atom is a proton. The nuclei of all the atoms are composed of proton and neutrons. To explain why the negatively charged electrons do not fall into the positively charged nucleus, Niels Bohr in 1913 proposed that the energies of the electron in atoms are quantized. This is they have only certain fixed values. Thus Bohr pictured the electrons are circling around the nucleus in orbit. Bohr's model of the atoms was successful in explaining the atomic spectrum of hydrogen atom. However, it failed to explain the spectra of multi-electron atom. Bohr model of atom also failed to explain the splitting of spectral lines in the magnetic field, that is known as Zeeman effect, as well as in electric field. The serious objection to Bohr's model of atom came from the new revolutionary ideas of de Broglie and Heisenberg, who introduced the concept of wave character of electron in addition to the particle character of electron, and pointed out that it is impossible to measure both the position and velocity of submicroscopic particles like electrons at the same time. Without a short time, a radically different model called the quantum mechanical model was proposed to account for new observation. In fact, the sophisticated quantum mechanical model of atomic structure was derived from the work of Louis de Broglie. Now we will discuss about the de Broglie idea of matter waves. In case of light, some phenomena like interference, diffraction, reflection, refraction can be easily explained by assuming light to have wave-like properties. However, there are certain other phenomena like black body radiation and photoelectric effect. They can be explained by assuming light to have particle-like character. Thus, light is said to be possess dual nature of a wave as well as the particle. This bold statement of dual nature was stated by Einstein in 1905. The credit to the discovery of the electron is the discharge tube experiment majorly goes to Sir J. J. Thomson. Various experiments performed on this radius consecutively proved that the particle of electron. In later experiments, the mass of the electron was determined to be 9.1 into 10 raised to power minus 31 kilogram. Even in Bohr model of atom, the electron is treated as a particle. It was only in 1924 Louis de Broglie, a French physicist, suggests that electron can also possess a dual character of wave and particle. Just as in the case of light, this laid the foundation of new subjects called the wave mechanics. In other words, the wave association within matter is called matter wave. Thus, according to the de Broglie, all material particles in motion possess wave characteristics. The de Broglie showed that just as electromagnetic wave could be treated as a stream of particles, photons, moving particle could also exhibit wave-like properties. Thus, it is important to picture electron either as particle as a wave. Before we take up the detail of this chapter, we are appropriate to know that interesting aspect of wave particle Sir John Thomson got the Nobel Prize for proving the electron as a particle. His son G.P. Thomson received the Nobel Prize for proving electron as a wave. It is indeed very interesting and existing. According to the de Broglie wavelength associated with a particle of a mass moving with velocity is given by the lambda is equals to h upon mass into velocity, where h is a Planck constant and m is the mass and v is the velocity. Total mv is equals to momentum of the particle. The wave associated with the material particle are called the matter waves. The equation 1.1 is known as the de Broglie equation. Derivation of de Broglie relationship. By combining the mass energy relationship proposed by the Max Planck and Albert Einstein, the de Broglie relationship can be derived. According to Planck, a photon of light having energy E is associated with the wave of frequency, where mu is equals to E is equals to h mu. According to the Einstein, mass and energy are related to E is equals to mc square, where c is the velocity of light. The equation h mu is equals to mc square. Mu into lambda is equals to c, where hc upon lambda is equals to mc square. H upon lambda is equals to mc. Lambda is equals to h upon mc. This equation is valid for a photon. De Broglie suggested that in substituting the mass of a particle m and its velocity v in place of velocity of light, see the equation can be lost also used in case of material particles. Thus, the wave of the material particle is equals to lambda is equals to h upon mv. This equation is known as de Broglie equation. In other words, h is equals to in other words, lambda is equals to Planck constant upon momentum, where h is a constant, then lambda is inversely proportional to the momentum. It means that the wavelength is inversely proportional to the momentum of the particle. Significance of the de Broglie relationship. Although the dual nature of matter is applicable to all particles, but it is significant for the microscopic bodies. For larger bodies, the wavelength of the associated waves are very small and cannot be measured. Therefore, practically all the larger bodies are said to be have no wavelength. Thus, any material body can have the wavelength but is measurable or significant only the microscopic bodies such as electron, proton, atom or the molecules. De Broglie equation and the angular momentum. De Broglie equation can explain successfully the Bohr's postulate regarding the angular momentum of the electron. If we recall, Bohr's model postulates that the angular momentum of an electron moving in a particular orbit is quantized, that is, it has definite values which are integral multiple of h upon 2 pi. However, according to the Broglie concept, electron is not only a particle but also possesses the wave character. Thus, in order that the wave may completely phase, the circumference of the orbit may be integral multiple of wavelength. 2 pi r is equals to n into lambda, where lambda is equals to 2 pi r upon n, where r is the radius of the orbit and n is the integer. However, according to Broglie equation, lambda is equals to h upon mv. 2 pi r upon n is equals to h upon mv. 2 pi r is equals to n into h upon mv. On rearranging, we get mvr is equals to n into h upon 2. Heisenberg uncertainty principle. In 1927, Werner Heisenberg pointed out that one of the cannot measure accurately both the position and the velocity of a microscopic particle. On the basis of the observation, Heisenberg put forward the principle known as Heisenberg uncertainty principle, known to the principle. It is not possible to determine precisely both the position and the momentum velocity of a small moving particle with accuracy. Consider a photon of light incident on a particle. If the particle is of reasonable size, its position or the velocity will not be altered by the impact of light photon, but it is not so when particles is extremely minute, such as an electron. It will suffer a change in the velocity as well path due to impact of even a single photon. The path and velocity of an electron after the impact of photon may be quite different from the original path and velocity. In view of Heisenberg principle, the Bohr's model in which electron is considered as particle moving in the definite orbital well defined path does not hold good. It is thus more accurate to say the electron associated with definite energy than to say it is belong a particular orbit. Mathematical expression for the uncertainty principle is delta x into delta p is greater than or equal to h upon 4 pi, where delta x is uncertainty in position and delta p is in uncertainty in momentum. The sign greater than or equals to means that the uncertainty can never be less than h upon 4 pi. If delta x is small, then the position of a particle is measured accurately. The delta p would be large and thus the uncertainty in momentum will be large. On other hand, if delta p is small, the momentum of the particle can be measured accurately and the uncertainty in the position that is will be large. In brief, it is impossible to determine simultaneously the position and the momentum of a microscopic particle with absolute accuracy or certainty. Werner Heisenberg, the German physicist, won the Physics Nobel Prize in 1932 for this contribution. Now we are study about Schrödinger wave equation. Erwin Schrödinger proposed a simple idea that if the electron behave like a wave, it should obey the classical equation of wave motion. On substituting de Broglie wavelength given is the by the relation lambda is equals to h upon mv into the classical wave equations, Schrödinger obtained an equation that describes the three-dimensional wave motion of the electron. This equation, popularly known as Schrödinger wave equation, can be written in the simplest form as del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square plus 8 pi square m upon h square into e minus v psi is equals to 0, where x, y, z are the space coordinate, m is the mass of electron, e is the total electron, v is the potential energy, h is the Planck constant, psi, a Greek letter spelled psi, is the amplitude of the electron wave and is called wave function. It is important to note that the wave function psi is dependent upon the variable x, y, z is expressed as psi x, y, z. For convenience sake, it is simply written as psi only. Del square psi upon d del x square represent the second derivative of psi with respect to x. Del square psi upon del y square represent the second derivative of psi with respect to y, and del square psi upon del z square represent the second derivative of psi with respect to z. Solution of Schrödinger wave equation. Like other differential equations, the Schrödinger wave equation has many solution values of psi. However, all the solutions do not have physical significance and thus are not acceptable. The first requirement in applying the Schrödinger wave equation to particular system is to obtain a suitable expression for psi showing how the wave amplitude varies with distance along the xyz axis, and then to derive the solution of differential equation only those wave functions which satisfy certain conditions and which have the physical significance are acceptable. These are called the eigenfunction on the system. The corresponding energy to the eigenfunction is called eigenvalues. Condition which a wave function psi must satisfy before it is acceptable are: psi must be single valued, it must have a single value at any point in a space. Second, psi must have finite value. Third, psi must be continuous. Fourth, psi must be normalized, that is the probability of finding the electron taken overall. The space must be unity, means 1. Fifth, psi must be 0 at infinity. Therefore, it can summarize that the wave function of Schrödinger wave equation must be single valued, finite, continuous, and normalized. Eigenfunctions are the solution of Schrödinger wave equation which have physical significance and correspond to their certain definite energy values. These waves functions represent the orbitals. Eigenvalues, these are the definite value of total energy for the solution of Schrödinger wave equation that have physical significance. Significance of wave function. Schrödinger wave equation is a second order partial differential equation. The symbol psi is the equation in commonly called wave function, and it represents the amplitude of electron wave. You must come across different kind of waves such as water waves, sound waves, electromagnetic wave. In case of water waves, it is easy to understand the amplitude of the wave. The amplitude of water wave is given by the distance water moves up or down the mean while level. But there is no direct way of measuring the amplitude in case of sound and electromagnetic wave. In case of light waves, the square of amplitude of the wave at a point is proportional to the intensity of light. Intensity of light is directly proportional to the amplitude square. It means that the intensity of light is proportional to the density of photon at the point in space. If we apply the same concept to electron wave function, the square of the amplitude of electron wave psi square should mean the intensity of finding electron at that point. According to uncertainty principle, the position of electron can be determined with certainty. It means psi square determines the probability density of finding the electron at the point. This means that when psi square is high, electron density is high, the probability of finding the electron is high. If psi square is low, then electron density is low and the probability of finding electron is low. There are two types of wave function, normal and orthogonal wave function. Now we will study about normal and orthogonal wave function. We have learned in the earlier section that psi represents the amplitude of the electron wave, whereas psi square determines the probability density of finding the electron at a point. If we sum up all the probability of finding the electron over the whole space, it must be unity. A wave function that satisfies all above conditions is said to be normalized. Mathematically, if it can be expressed as positive infinity to negative infinity psi square dot dx dot dy dot dz is equals to 1. It means that if we are integrate psi square with respect to volume element represented by the product of dx dy dz from from negative infinity to positive infinity, that is over the whole space around the nucleus, it should come out to be unity. This condition of normalization is reasonable in view the in fact that the probability must become certainty somewhere is the universe. However, we have learned that psi square is proportionally to the probability of finding the electron in a given volume element. In such a case, the wave function can be normalized by multiplying by a constant n so as to give a wave function which is always equals to probability in a given volume element. The product to the constant n and the wave function is called to the normalization constant. Mathematical representation. Negative positive infinity to negative infinity n psi product to n psi dx dy dz is equals to 1. The normalization constant n can be evaluated from the above expression. Orthogonality. A particular wave function must be different from all other wave functions over the whole space. The chosen function should be independent of the other, that is, they should be orthogonal to each other. This is because if two particles had non-orthogonal wave functions, then their description would not be unique is one as wave function could be described in the terms together. Therefore, we have functions should be independent on another. In other words, they should be orthogonal to one another. Mathematically, the condition for the orthogonality is that product of two wave functions when integrated over the whole space should be equals to 0. That is, if there are two wave functions psi1 and psi2 with complex conjugates psi1 star and psi2 star respectively, then for being orthogonal to one another, integrate psi1 psi star 2 dx dy dz is equals to 0 and integrate psi2 with psi star 1 dx dy dz is equals to 0. If psi1 and psi2 are real functions, integral psi1 psi2 dx dy dz is equals to 0. Psi star 1 is equals to psi1 and psi star 2 is equals to psi2. When they both the equation is equals to psi1 psi star 1 dx dy dz is equals to 1. And integral of psi2 psi star 2 dx dy dz is equals to 1. They are said to be normalized wave functions. The wave functions which are both normalized and orthogonal are called the orthonormal functions. Now we are studying about quantum numbers. The hydrogen atom is the simplest example of one electron atom. Other example of an electron ion are helium positive, lithium 2 positive, and ions in which all but one electron has been removed. In order to solve Schrödinger wave equation for hydrogen, a set of three constant or numbers must be defined. These numbers are called quantum numbers. These are designed as N, L, M. In addition to these three numbers, the fourth quantum number designed as S is also required to specify addition to these three numbers. The fourth quantum number designed as S is also required to specify the spin of the electron around its axis in addition to motion around the nucleus. A set of four quantum numbers which determines completely the position and energy of the electron in an atom are called numbers. These are principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. Now we are studying about principal quantum number. It is the most important quantum number as it determines the principal energy level or shell to the which electron belongs. It is denoted by the letter n and can have the integral value starting from 1 to infinity except 0. That is, n is equals to 1, 2, 3, 4 and infinity so on. The various principal energies level or shell are also designed by the letters K, L, M, N, etc. starting from the nucleus. Now the next is azimuthal or angular quantum number. Azimuthal quantum number refers to the subshell or sublevel in a given principal energy shell to which the electron belongs. It is also named as secondary quantum number and it is designed by the symbol L. This quantum number gives the energy of the electron due to angular momentum of the electron. The magnetic or of the angular momentum of the electron is related to L by the expression. Angular momentum is equals to root L into L plus 1 product h upon 2 pi, where L is equals to 1, 2, 3, so on n minus 1. Each value of L represents a particular subshell or sublevel. If n is equals to 1, L can have only one value, that is 0. It means that there is only one type of subshell. In other words, for n is equals to 1, the subshell and shell are really identical. If n is equals to 2, L can have two values, 0 and 1. It means that electron with n have two subshells. If n is equals to 3, L can have three values, 0, 1, 2. It means that an electron with n is equals to 3 has three subshells. If n is equals to 4, it can have four values, 0, 1, 2 and 3. It means that an electron with n is equals to 4 has four subshells. Thus, for each value of n, there are n different values of L. The different values of L are coded the letter SPDF depending upon the value of L. The designation of SPDF are the characteristics of the spectral lines found in spectra: S sharp, P principal, D diffused and F fundamental. Now we studied about magnetic quantum number. This quantum number describes the perfection orientation of the electron in the presence of magnetic field. An electron is a charged particle and momentum of electron around the nucleus generates an electric field. This generated electric field in turn produces the magnetic field. Now when an external magnetic field is applied, there is an interaction between magnetic field produced by the flow of the electron and the external magnetic field. This results in the electrons in a given subshell to orient themselves in some preferred region of space around the nucleus called the orbitals. Thus, the magnetic quantum number determines the number of preferred orientation of the electrons present in a subshell. Since each orientation corresponds to the orbital, therefore the magnetic quantum number determines the number of orbitals present in any subshell. The magnetic quantum number is designed by M. The value of M depends upon the values of L. For a given value of L, M can be integral values from starting to minus L to 0 plus to 0 plus L, negative to 0 to plus L. Thus, for any value of L, M can have a total of 2L plus 1 values. Now the next topic is spin quantum number, which is a part of quantum number. So far we learned the electron is continuously revolving around the nucleus. In addition, the electron is revolving around its own axis. The spinning of electron also produced a small magnetic field. The electron can spin in two ways, either clockwise or anti-clockwise. There is an additional quantum number that describes the spin orientation of the electron and is called the spin quantum number. It is generated by S. For any particular value of magnetic quantum number, spin quantum number can have two values, that is either positive 1 by 2 or negative 1 by 2, or the positive or negative sign before 1 by 2 indicates the direction of spin, clockwise or anti-clockwise. Sometimes the spin values are represented by the arrows in the opposite direction. The spinning electron behave like a micromagnet, and the magnitude of angular momentum due to the spin is given by expression. Angular momentum due to spinning of electron is equals to h upon 2 pi under the root s into s plus 1. Where in the spin of electron, it may be added that the spin quantum number was not obtained from the solution of Schrödinger wave equation. This was introduced independently to account for the spin orientation of the electron around its axis. In summary, the complete wave function represents an orbital in which the radial part gives its size and the angular part determines its shape. The molecular geometry can be better understood through the wave mechanical model of electrons, the wave distribution around the nucleus. In the previous section, we must shown the total wave function in the spherical polar coordinates can be collectively expressed as psi r comma theta comma phi is equals to r n l bracket r radial part, l m theta dot phi m theta angular part. The mathematical expression of the total wave function psi can be easily understood if we plot the radial r and the angular theta and phi parts of the wave function separately. Radial wave function. The radial part of the wave function r gives the distribution of the electron as the wave as the function of the distance from the nucleus. It depends primarily on the values of quantum number n and l. The mathematical expression of the radial part of the wave function for 1s, 1, 2s and 2p orbitals for the hydrogen atoms. In this figure or in this diagram, the orbitals for the hydrogen and hydrogen-like atom are given in table 1.2. This is the table 1.2. In this, E is base of natural logarithm, Z is the atomic number, Bohr radius, A naught, and the N is the principal quantum number. Now, angular wave function. The angular wave function predicts the shape of the electron cloud and its orientation in the shape as mentioned earlier. The angular wave function depends on L and M values. The shape of orbital depends upon angle theta and phi, which determine the geometry. The angular part of wave varies depending upon the type of orbital involved, that is S, P, D and F. Thus, the probability of finding the electron in any given direction from the nucleus without reference to its distance from the nucleus can be estimated. Mathematically, expression for angular wave function for S, P, D orbitals are in 1.3. This is the figure 1.3. The electron cloud may have spherical or non-spherical symmetry depending on the value of L and space. S orbital L is equals to 0 has only one orientation is spherical symmetry. P is equals to L is equals to 1 has 3 orientation. D is equals to 2 have 5 orientation depending upon the various values of M for the corresponding values of L. Shape of orbital. The actual wave function for the electron is in hydrogen atom is expressed Product of radial part and the angular part. The angular part of the wave function depend upon the direction theta and phi, whereas the radial part depends upon the distance from the nucleus. The part of the physical significance of the radial part has already been discussed in detail. Let us now discuss angular part of the wave function determines the shape of the orbital. If you recall, radial part determines the shape of the orbital. For s orbital where L is equals to 0, the value of m is equals to 0. There is no possible orientation. This means that the probability of finding an electron in the same old direction at a given distance from the nucleus. It should therefore be spherical in a shape, because a shape can be defined completely by a single value, that is radius. Hence, as orbital are non-directional and spherically symmetrical about the nucleus. The size of orbital depends upon the value of principal quantum number. The larger value of and the larger value of orbital. Therefore, 2s orbital is larger than 1s orbital. Both these orbitals are non-directional and spherical in shape. An important feature of 2s orbital is that there is a spherical shell within this orbital where the probability of finding the electron is 0. This is called the node or nodal surface. The node corresponding to nearly 0 value of probability in finding the two maximum in the radial probability distribution curve. Thus, a 2s orbital differs from 1s orbital in being larger in size and having a nodal surface. Each s orbital has a region of high probability representing by spherical shell equal to n. For example, one s orbital has 1, 2 s orbital has 2, and 3 s orbital has 3 region of high probability. Shape of p orbital. For p orbital, there are three values of, namely -1, plus, +1 and 0. It must be p. It means P subshell can have three possible orientations. These are represented by Px, Py and Pz. The distribution of electron density of an electron in the 2p orbital is not distributed in a symmetrical manner. In an s orbital, their orbitals are equal in energy. Each p orbital consists of two lobes symmetrically about a particular axis. Depending upon the orientation of the lobes, these are denoted by 2px, 2py and 2pz according to the symmetrically about xyz respectively. Two lobes of each orbital are separated by the nodal plane. The P is a dumbbell shaped and the directional characters. The probability of finding the electron in both the lobes, the p orbital higher level, have similarly shaped although their size is bigger. 3px orbital in larger in size than 2px orbital has two lobes on each side. The 3py and 3pz are also in the shape of d orbital. For d orbital, the value of azimuthal number L is equals to 2. Thus, L is equals to 2, where the phi possible orientation corresponding to the allowed value of m. These are m is equals to -2 plus 1 -2 -1 0 plus 1 and plus 2. Thus there are 5 orbitals in each d orbital. For 3d orbital, these are designed as 3dx, 3dy, 3dyz, 3dzx, 3dx square minus y square and 3dz square. All these orbitals are degenerated, that is, they possess the same energy. However, these orbitals differ in orientation in space as shown in figure. The salient features of these orbitals are: first, the three orbitals, namely dxy and dyz and dzx, consist of four lobes of high electron density in x, y, yz and zx planes respectively. Each lobe bisect the principal axis into two equal halves. These are double dumbbelled in shape. And the 3dx square minus y square orbital has four lobes of high electron density along the principal axis x and y. The dz square orbital has the unique shape. It has two lobes along the z with the ring of electron density around the nucleus in the xy plane. In fact, dz square is formed by the linear combination of two orbitals 3d y square minus z square and 3z square minus x square, each of the which have four lobes along the corresponding axis. Energy level diagram. Schrödinger wave equation has successfully been solved. Exactly, the hydrogen atom which has only one proton and one electron. Other commonly example of hydrogen like atom and lithium plus helium etc. However, difficulties arise in case of multi-electron system. In such case, approximate methods are used to find the solution from which calculation of energy levels for orbital are made. The energy value of various energy levels obtained from the solution of Schrödinger wave equation have been found in the consistency with the experimental value obtained by the spectra of hydrogen or hydrogen-like atom. The energy level diagram upon the principal quantum number and the independent of the value of second quantum number L. Thus all the subshell in the principal cell have same energy values. As an example, 2s and 2p subshell have the same energy. Similarly, 3s, 3p, 3d subshell associate with the third shell n is equals to 3 have same energy. Similarly, in the fourth cell n is equals to 4 the subshell as pdf have same energies. As already pointed out, in some case multi-electron system, the solution of Schrödinger wave equation are not exact. In such a case, approximate methods are used which give nearly accurate solution. The energy values of various energy levels are calculated. The energy level diagram for multi-electron system is shown in figure. Important feature of energy level diagram multi-electron atoms are: in the hydrogen atom, the value of principal quantum number L alone determines the energy of orbitals. All the subshell of a shell in a case of hydrogen have the same energy. In case of multi-electron atom, the energy of various level depend upon the principal quantum number n as well as on the angular quantum number L. Thus all the subshell of a shell in case of multi-electron system have different categories. In case of multi-electron atom, for the same of n and the higher of value of n, the higher is the energy. For example, 2p orbital n is equals to 2 and L is equals to 1 has more energy than 2s where n is equals to 2 and L. Now we are study about Aufbau principle. Aufbau principle is a German word which means building up. Some people prefer to call the building up principle when it is an equivalent German name. The Aufbau principle, it is a procedure of filling up electron in various orbitals according to the principle. The electrons occupy the lowest energy orbitals available to them in the ground state of an atom. It means that the electrons enter the orbitals in the order of increasing energies. The lowest energy orbitals available in being filling up first. The case of multi-electron atom, the following sequence of filling the electron as the increasing order of energy is followed: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. The energy of an orbital is determined by the quantum number n and L. Therefore, the sequence of filling proceed according to the following rules. Orbitals are filled in according of increasing value of n plus L. Orbitals having the same value of n plus L, the orbital having lower value of n is filling up first. As an example, 3s orbital in lower in energy than 3p orbital. Similarly, 2p orbital and 3s orbital have the same n plus L value, but 2p orbital associated with lower value of n then therefore has lower energy than 3s orbital. This important n plus L rules are also known as Paul-Bury's rule. It also helps to explain the certain orbital with higher value of n but lower value of L possess less energy than orbital with lower energy of n, higher value of L. This is the diagram for the Aufbau principle. Now the next principle is Pauli's exclusion principle. An important principle was proposed by Pauli in 1925 which described the number of electrons that energy level can accommodate. According to the principle, no two electrons in an atom can have the same set of all four numbers. It clearly means that for two electrons in the same orbital, three quantum number may be same but the fourth must be different. Application of these principle also help in determining the maximum number of electrons that can be present in any given energy level. Electrons with the same set of value of an L and M belong to the same orbital. For example, the K shell for which n is equals to 1, L have is equals to 1 value, L is equals to 0, M can have value M is equals to 0. As a result can be negative 1 by 2 or positive 1 by 2. This means although n, L, M, N are the same for the two electrons but their spin quantum number are different. On similarly lines, L shell for which n is equals to 2, L have two values, L is equals to 0 and L is equals to 1, where M can have one value for L, L is equals to 0 and that is M is equals to 0, and their three values of L is equals to 1 is M is equals to minus 1 plus 1 and 0. For each value of MS can have two values plus minus 1 by 2. The 8 possible value of quantum number corresponding to L shell are as follows. It is evidently that L cell can accommodate 8 electrons. 2 in L is equals to 0 L subshell and 6 in the L is equals to 1 subshell. Pauli's exclusion principle can also stated as no more than 2 electrons may occupy any given orbital. When 2 electrons do occupy one orbital, their spin must be paired. An orbital can have more than 2 electrons. If an orbital has 2 electrons, then must have the opposite sign. Limitation of above principle. Above principle is quite useful to formulate the ground state electron configuration of atoms. Although electronic configuration based upon above order of filling agree mostly in those derived experiment by the various spectroscopic studies, yet they are quite of new expectations. This happens mostly in the cases where the subshell involved the configuration are exceedingly closely spaced are there likely to exchange positions. Some of the above limitations are listed below. Electronic configuration of atoms on ionization. The above principle cannot be used to predict electronic configuration of atom on ionizing. It fails to tell which electron are the removed ion is formed from an atom. For example, according to above principle, the electron configuration of iron Z equals to 26 is 1s2 2s2 2p6 3s2 3p6 4s2 3d6. While building the configuration of an atom of iron is the last electron added to the 3d orbital. Electronic configuration of lanthanoids. Our principle cannot explain the electronic configuration of lanthanoids. Z equals to 57 to 71. In fact, the sequence of filling electron orbital in the case of lanthanoids deviates slightly from the prescribed arrangement shown in figure. After the filling of 6s orbital in case of barium, Z equals to 56. The next electron in lanthanum should be filled in 4f subshell. In fact, does not happen. Rather, the next electron enter the 5d subshell. The electron configuration thus become La is equals to xenon 6s2 5d1. However, from the lanthanum Z equals to 57, the filling of electron is the next element size 5871. Cerium to deuterium occurs in the 4f shell, and even the previous electron in 5d orbital is also shifted to 4f subshell. The filling of 5d restart only after the 4f subshell is completely filled with La Z equals to 71. Electronic configuration of actinides. The electronic configuration of actinides Z equals to 89 to 103 can also not be predicted correctly by above principle. The sequence of filling again derives from the normal assigned trend. Immediately after the filling of 7s orbital in case of radium, the next electron in actinium Z equals to 89 should enter the 5f subshell. However, the electron enter in the 60 subshell. The electronic configuration the subshell AC is equals to xenon 7s2 and 61. This reason for such exceptional configuration is attributed to small energy difficult between the 4f and 5d subshell, whereas the electron transfer occurs easily. The shielding and the effective nuclear charge. Most of the physical and chemical properties of the element can be explained on the basis of electronic configuration of element. As the electronic configuration help in explaining many properties, some way the role of nuclear charge is accommodate for the explaining of the periodicity of many properties. As an example, consider the behavior of ionization energy in the periodic table. It is known the magnitude of ionization potential depends upon the following factors. First, the size of atom. Second, the nuclear charge. Third, the screening effect of the inner shells. Fourth, the extent to which the outermost electron penetrates into the charge cloud set up by the inner lying electrons. The larger the size of atom, the less slightly are the valence electron held by the positive charge on the nucleus, and lower is the value of ionization energy. The greater the charge of the nucleus, more difficult is to remove an electron from the atom and hence greater than in ionization energy. The existence of the inner shell of the electron between the valence shell and the nucleus to a certain extent shield the outermost electron from the nucleus, because the attractive force of the nucleus on the electron is partially counterbalanced by the repulsive force from the inner shell of electron. Thus, an increase in the number of electrons in inner shells tends to decrease the ionization energy. Thus, the reduction of the nuclear charge or pull on the outermost electron of an atom by the intervening electron is called the screening or shielding effect. The greater the number of electrons in the inner shell, greater the shielding effect. The magnitude of the screening effect does not depend upon the number of electrons on inner shell, but mainly upon the type of orbital occupied by the electron. The degree of penetration of electron is given principal quantum number level decrease in the order S greater than P greater than D greater than F. Now we are study about Slater's rule. In 1930, J.C. Slater proposed a set of empirical rules to understand the concept of effective nuclear charge. He proposed a formula that related Z effective to actual nuclear charge Z. Z effective is equals to Z minus S, where S is the Slater's screening constant. Slater derived a series of empirical rules for calculating the value of S. It is possible to evaluate the shielding or screening constant, which is defined as the measuring to the extent to which the intervening electrons shield the outermost electron from the nuclear charge. From the knowledge of screening constant, the effective charge is calculated by subtracting it from the nuclear charge. The Slater's rule for calculating shielding constant are: the electronic configuration of the element in first written in the following order and grouping: 1s, 2s, 2p, bracket close, bracket start, 3s, 3p, bracket close, brackets in bracket 3d, in bracket 4s, 4p, in bracket 4d, in bracket 4f, in bracket 5s, 5p, in bracket 5d, in bracket 5f, and so on. Electron in any group higher in sequence than the electron under considering contributed 0 to the screening constant. Third, electron in the same group contributing 0.35 electron excepting in the 1s group, which is contribute 0.30 instead of 0.35. Fourth, for an electron in the ns and np orbital, all electron in n-1 cell contribute to 0.85 per electron, and all electron in next inner shell, that is n-2 and lower shell, contribute as is equals to 1.00 each. Fifth, for an electron in Nd or Nf orbital, all electron in lower groups contributed as is equals to 1.0. Calculate the shielding constant based on Slater's rule. The electronic configuration is written as 1s bracket in bracket 2s2p in bracket 3s3p in bracket 3d in bracket 4s4p in bracket 4d in bracket 4f in bracket 5s5p and so on. Application of Slater's rule. The concept of effective nuclear charge is quite useful and important in many respects. Some of its applications are the following. It helps justifying the filling of 4s first then 3d orbitals. Second, it explains why 4s electrons has last prior to 3d electron while forming of cation in transition elements. Third, it explains why a cation is always smaller than the parent atom. Now the limitation of Slater's rule. Slater's rule are very useful for calculating the effective nuclear charge for atom and ions. However, it has several limitations which are detailed below. Both s and p orbitals are grouped together for evaluating the effective nuclear charge. Fault. This is a faulty assumption because the radial probability distribution curves for n given n indicates the higher penetration of s as compared to p. According to Slater's rule, all the electrons, irrespective of s, p, d, and f orbitals present in shell lower than n-1 shell, the n electrons will equal contribution of 1.00. This is not justified because energetically different orbitals cannot contribute easily. Third, Slater's rule are less reliable, especially in case of heavier elements. This chapter is completed. Thank you.